Hello. Today we're going to have a look at the second part of the interference part of the waves unit at Higher Physics, and we're going to look at a thing called diffraction gratings. Now, a diffraction grating is basically a piece of glass with lots of tiny transparent slits in it. And each of those slits can be very, very, very close together so that when a light ray passes through it, the light ray is split into multiple coherent beams. Remember from the last video, a coherent wave is one that, or a multiple coherent waves are ones which have the same wavelength, the same frequency, and the same phase relationship. Now, usually these diffraction gratings have got hundreds of tiny grooves in every millimeter of their surface. So usually they're defined as how many lines per millimeter they have. But we usually need to know how far apart the lines on the grating are. So if you need to convert from how many lines per millimeter to the spacing of the grooves on the grating, then we need to divide 1 millimeter, which is 1 times 10 to the power of minus 3 meters, by however many lines there are per millimeter. Keep that in mind because we'll need that when we try some examples later on. Now, here's what happens. In this image, you can see a laser on the far right producing a beam of light of wavelength lambda. This is a monochromatic beam, which means that all the photons are identical, they're the same color, same wavelength. And it's shining onto the diffraction grating there with a certain separation of lines on it. And it's producing an interference pattern on the other side. So right along the center, we get what's called the central maximum, where there's constructive interference of that light occurring. But then either side of that, we've got the first order maximum. And then either side of that, we have the second order maximum, and so on and so on. Now, in between the first order, the zero order maximum, the central maximum, and the first order maximum, we have an angle. And that angle creates part of a right angled triangle. Now, if we were to look at it head on, it would look a bit like this, where the central maximum looks like a red spot, and then either side of that, there's a slightly dimmer red spot, which is the first order maximum. And then either side of that is a slightly dimmer red spot, which is the second order maximum, and then the third order maximum, and so on and so on and so on, with increasingly dim spots. Now, how does this look? Well, in this image, we've got the laser beam coming from left to right through the grating and creating this interference pattern on the screen on the far right. And we get this series of red spots. Now, you can see there, I've drawn a triangle representing the zero order maximum, so the m equals 0 maximum, and the m equals 1 maximum with the angle in between. Now, constructive interference occurs where d sine theta equals m lambda. Now, what does that mean? D is the spacing of the slits on the grating, usually a very small number. Sine theta, well, theta is the angle between the central maximum and the bright spot that we're interested in. M is the order of the maximum, so it might be m is 1, 2, 3, 4, and so on. And lambda is the wavelength of the light. So here's an example. A grating with 300 lines per millimeter is used with a spectrometer and a source of monochromatic light to view an interference pattern as shown below. So you can see here in the diagram the monochromatic light source, it's probably a laser on the far left, shining light on the grating in the center, and then it's creating a straight through direction, so that's the first order or the zero order maximum, and then there's a first order maximum, m equals 1, and then there's a second order maximum, m equals 2, which is where we're viewing this red spot now, or the spot now. says the second maximum of interference is observed when the telescope is at an angle of 24.5 degrees. Calculate the wavelength of the light. So, first thing we need to know is how far apart are the lines on the grating. So, the number of lines per millimeter is 300 lines per millimeter. So to find how far apart the lines actually are, I take 1 millimeter, which is 1 times 10 to the power of minus 3 meters, and I divide that by 300. And that tells me that the distance between the grooves on the grating is 3.33 times 10 to the power of minus 6 meters. So now I know my D value. Now I can work out the wavelength using the diffraction grating formula, which is d sine theta equals m lambda. So in this case, d is my spacing on the grating, which is 3.33 times 10 to the power minus 6. Sine theta is my angle, so sine in this case 24.5. M is my maximum number. In this case, it's the second order maximum. So my M number is 2. And lambda is the wavelength I'm trying to find out. So let's do a little bit of algebra and rearrange that formula. And then we get a value for our wavelength. 6.91 times 10 to the power minus 7 meters. So we'd be right in the really deep red. 691 nanometers, as it were. Now, that's what happens with monochromatic light, light of all one wavelength. What happens when we get light of multiple wavelengths? Well, white light is made up of a complete spectrum of visible light. So when we look at that through a diffraction grating, we get something that looks a bit like this. So rather than a series of single coloured spots, in the centre we get a central maximum that is white, as is the white light that produced the spectrum to begin with. So m equals 0, we get a constructive interference of white light. However, at all the other maximum, so the m equals 1 maximum, the m equals 2 maximum, m equals 3 maximum, and so on, we get a series of spectra. And you can see here the order of the colours in the spectrum, with the violet end of the spectrum in the centre, and then the other colours working outwards from there. So the usual visible spectrum, red, orange, yellow, green, blue, indigo, violet, but with blue closest to the middle and red furthest out. And that repeats for each maximum as we work our way outwards. So why do we get the central maximum that is white, and why do we get this spectrum for all the other maximum? Well, here we have our formula, d sine theta equals m lambda. Now, if we rearrange that formula, we get theta equals sine to the power of minus 1 of m lambda over d. Now, what that means is that the angle where constructive interference is achieved depends on the wavelength of the light that we're dealing with. Now, at the center maximum, m is 0. So theta would also be 0 at the center maximum, regardless of the wavelength. So when we're at the center maximum, the wavelength doesn't matter. We get constructive interference at the same place. However, where m, our maximum number, is 1, 2, 3, or whatever, the angle theta depends on the wavelength. And the bigger the wavelength, the bigger the value of theta. So we end up with something a bit like this. So the angle between the center to violet, the first violet band, is the smallest because the wavelength of violet light is the smallest. The angle between the center maximum and the first red band is bigger because the wavelength of red light is bigger. We need to keep in mind these approximate wavelengths. Red, green, and blue light. Red has got the longest wavelength of around about 700 nanometers. Blue has got the shortest wavelength of about 490 nanometers, and green is somewhere in between. Try and remember these values, but if you forget them, there is some example wavelengths of red, blue, and green given in the datasheet on the inside cover of your exam paper. So if you forget them, you can always find them out there. So here's an example using white light. In an experiment, a ray of white light is incident on a grating. And we can see the white light coming in from the left, hitting the grating, and then creating this interference pattern on the screen on the far right. And the center maximum along the dotted line would be white, and then the first order maximum and then second order maximum are spectra. It says the angle between the center maximum and the second order maximum for red light is 19 degrees. The frequency of this red light is 4.57 times 10 to the power 14 hertz. Calculate the distance between the slits on the grating. So, first thing we need to do, well, our formula for working out diffraction gratings is d sine theta equals m lambda. Here, we want to know the distance between the slits on the grating, which is d. Now, in order to work that out, we need to know sine theta, which is the angle, which we're given, m, which is the order number, which we're also given, and wavelength, which we're not given. We need to work out the wavelength first of all. So casting our mind back to National 5, we remember we have this formula, V equals F lambda. And as we're given the frequency of the red light, and as we know the speed of light, we can put those numbers into that formula. Speed of light, 3 times 10 to the power of 8, equals the frequency of the light, 4.57 times 10 to the power 14, times lambda, a little bit of rearranging, and we get a value for the wavelength of the light of 6.56 times 10 to minus 7 meters. So now we've got all that we need. So let's put it all into our formula. D sine theta equals m lambda. So D is what we're trying to find out. The angle is 19 degrees, so sine 19. And that's the angle to the second order maximum, so m is 2. And the wavelength, we just worked out, 6.56 times 10 to the minus 7. A little bit of rearranging, and we get a value of the distance between the slits on the grating of 4.03 times 10 to the minus 6 meters, basically 4 micrometers. Now, part 2, it says, explain why the angle to the second order maximum for blue light is different to that for red light. Well, we just explained that because the wavelength of blue light is different to that of red light. In fact, blue light has a shorter wavelength than that of red light. And since if we rearrange our diffraction grating formula, we get sine theta, the angle, equals m lambda over d, a smaller wavelength, smaller value of lambda, will mean a smaller angle to a certain maxima. Okay, so that's a basic run through of the theory of diffraction gratings for our higher physics. So I hope you found that quite useful. In the next video, we're going to move on and have a look at the idea of refraction of light. Until then though, thank you for listening, and I'll talk to you again after a while. Bye for now.